Okay, so let's get started. So we'll finish the course with a discussion about random walks. Riaz has already taken you through most of that. So I'm going to go quickly, when we get to the theory part, I'm going to go quickly through that since that should just be a review. And my interest here is what are the tools that we can use to analyze a random walk and exactly what the model is. All right, so one model, for example, for stock price is to say that you start at some point and then you have an equal probability that it can move up or down by a certain amount. And then you just you track the evolution of that price, for example. And so that's an example of a random walk. Another example of a random walk would be something like Brownian motion. You have some small pollen particles suspended in water, and the way that it moves around is modeled as a random walk. Okay, so what we're going to do is I'm going to build, we're going to start with a very simple model, and then we're going to build some more sophistication into those. And as we go along, we will see what tools are available within Python for analyzing these walks and getting some results. Okay, so model one, the really simple one. Okay, so all you're going to do is you're going to be standing at some position called 0, and you're going to take a step to the left or to the right once. You're just going to flip a coin, let's say. So you have a 50-50 probability, and that will decide whether you move to the left or to the right. Okay. So imagine that we did this experiment. We were standing at the origin. We flipped a coin. If it was heads, we moved one step to the right. If it was tails, we moved one step to the left. Okay. So let me ask you, after that one coin flip, what was the probability that we are at a position 1? Right, we were at 0. Sorry, can you say that again?
0.5?
Yeah, 0.5. And being on the left was equally likely. Being at position -1 would be 0.5. And note that when we flipped the coin, we had decided that we were going to move based on the coin result. And so the probability of being at 0 is in fact 0. Okay. So that was the first model. That was really easy. Okay. And, you know, if we imagine that we were standing, say, on the number line, and we can move by a unit distance when we flip the coin, there's a probability 0 that we would be anywhere else. The only possibilities are, with a non-zero probability, are you could be at 1 with probability 0.5, or you could be at -1 with a probability 0.5. Okay. All right, so we're going to think about how we're going to code that. So if I have two possibilities, moving to the left or moving to the right, I could use 0 to mean that I'm going to move to the left, and I could use 1 to mean I'm going to move to the right. And I have to generate these possibilities randomly or with equal probability. Okay, so I need some sort of, you either have to write some sort of a utility within Python, or if I'm lucky, there's one already available. Okay, and there we go. numpy.random.randint of n, right? If you feed capital N into that, it will return a result 0, 1, 2, possibly 0 or 1 or 2 up to n-1 with equal probability. Okay, so how do we do this? Well, we'll import numpy as np. Our current location we'll call x is equal to 0. Now we have to decide whether the step is to the left or to the right. Okay, and so what we do is step is equal to np.random.randint of 2. That will return either 0 or 1 with equal probability. Okay, now if I actually want to then add, if it would be convenient if I take this output, which is from randint, which is 0 or 1, and I turn it into an output which is -1 or +1, because then I can add that to my x, and that result will tell me which location I'm at. Okay, so what I'll do is I'll say if step is +1, that's fine. I'd like it to be +1. But if it's 0, which I'm interpreting as being moved to the left, then I would like to turn that 0 into a -1. So I'll say that if step is the same as 0, then I would like step to be equal to -1. And then I will add that to my location x. And then x is wherever I would end up with. Okay. So if I run that, sometimes I'll get -1, and sometimes I will get +1. Okay. So is that code fine so far?
Yes, Professor.
Okay. Now that's taking a single random step is not interesting. Okay. So what if we'll go to a second model? I'll call that model 2. And we're going to step to the left or to the right, capital N times. Okay. So we're going to start from 0. Then from 0, you could end up at, you're going to flip a coin, equal probability of going to the left or to the right. So you started from 0, you flipped a coin, you could be at + or -1. And then if you were at +1, in the next coin flip, you could be at 0 or at 2. And if you're currently at -1, with the next coin flip, you could be at either 0 or -2. And we're just going to keep doing this n times. So any questions about that? Okay. So let me ask you. Supposing we took n steps randomly, either to the left or to the right, with equal probability. Okay. What is the probability that after n steps, you are at position +n? Starting from 0, after n steps, you're at position +n. What's the probability of that?
0.5 to the power n.
That's right. That's right. Because you'd have to take a step to the right, then another step to the right, then another step to the right. You'd have to have n steps to the right to get to n in n steps. And each step to the right is occurring with a probability of 1/2. So it's 1/2 to the n. Okay. All right. What's the probability in n steps you got to the position -n? What's the probability there?
0.5 power n. Again.
Yeah. Again, 1/2 to the n. It's an analogous situation. Okay. What if n was equal to 5? Right? So I did 5 coin flips. Starting from 0, I took these random steps to the left or the right. In 5 steps, what's the probability of being back at 0?
Zero.
Why?
Because there are an odd number of steps and you can either move up or down. So you, even at the best, if you're closest to zero, you'd either be at 1 or -1, never at 0.
Right. If you're starting from 0, then you have to take a certain number of steps away and then a certain number of steps back, the same number of steps back, right? Right, the number of right steps and the number of left steps have to cancel each other out so that, right? So you have to have the same number of steps to the left or to the right. So the total number of steps has to be even for you to get back to 0. So you cannot get back to 0 in an odd number of steps. So probability of getting back to 0 in an odd number of steps is 0. Okay. All right. What's the probability of being at I after j steps? It takes a bit of thought, but okay, so let me just suggest how you'd go about thinking about it. To be at position I in j steps means that you have to have been at position either I plus 1 or I minus 1 after j minus 1 steps, right? And then in order to be at position I plus 1 or I minus 1 after j minus steps, you have to have been, think about where you would have to have been at j minus 2 steps, and so on and so forth. So you can work out the probabilities recursively. Okay. All right, so let's say now that I wanted to simulate such a thing. I'm going to take n steps and I'm going to see where I end up. Okay, so what would I have to do? All right, you import numpy as mpy. Step, like I said, you want results which are, you want 2 possible results to the left or to the right. And then if you want to be able to add your result to the step, then I'll take the result of 0 and I'll change that to -1. And then you can return that to the set. So now, if n is 100, that's the desired number of steps. I'm starting from x is equal to 0. So what I'm going to do is 100 times, I'm going to get the step either to the left or to the right. I'm going to add it to the position x. Okay. And then I'm going to print the result. And well, you could have results in principle ranging from -100 to 100. On one run of this code, I got -4. Okay. All right. Now, if we're going to analyze our results, what would we like to know? We'd like to know things like, if I did the same experiment over and over again, what's the average displacement of 0? What's the probability of a final state of 7 compared to the probability of a final state of 50? And how often do I go through the same location? So if n is 100, for example, then I can only go through the location 100 once, right? With a probability of 1 over 2 to the 100. On the other hand, if I could, a location of something like, say, -2, I could imagine going through that many times, right? So Another thing that interests us is the number of returns to a particular state. Okay, so how do we estimate these? Let's say we should be able to actually work these out analytically. But if we wanted to just do the experiment, we want to do the simulation. And then how do we estimate these? Well, you do lots of runs, and for example, and you store the final state. So let's say you want the average displacement from 0. Then what you do is do a lot of runs. For each run, store the final state, and then extract the statistics. Okay. All right, so some useful methods that you built into Python for doing things like this. So NumPy has a mean method. You feed it an array, it gives you the mean of the array. It has a variance method. If you give it an array, it can give you a histogram. And matplotlib will plot histograms for you. Right, it has a feature for creating histograms. So all of these might be useful to us in this discussion. Okay, so import numpy as np, import matplotlib.pyplot as plt as we did before. We have the same get step function. Now what are we doing? We're doing as we did before, except we're going to do it n times. And each time we're going to be left with the result will be the final state in the random walk. Okay, so let's say that the number of steps in each walk is 1,000, and let's do 1,000 walks independently of each other. And every time we get to the end of the walk, we will put that end state into a list, which I'll call X list. Okay, so we do that n equals 1,000 times. Every time we do it, we append the final result to X list. Now we get out some statistics. So we'll take the mean, we'll take the variance, and the standard deviation is the square root of the variance. And we'll plot a histogram of the results which we stored in X list. Okay, so for one run, it looks something like this. The final mean position was 0.068. The variance was about 1,085, and the standard deviation is 32.9. Okay, and the histogram of final results looks like what you're seeing there. Okay. Now, what if I had, I don't know, what if I made it a walk of 10,000 steps and I did that 100,000 times? What do you think the histogram should start to look like?
The normal distribution curve?
Yeah, it should start to look like the normal distribution. Okay. All right. Let's see. Okay, so now let's say we wanted to apply a bit more of the probability that hopefully you remember from your probability course. Yeah, it's fairly simple. We can, if you don't remember it, this will be a useful review for you. So let's say U1, U2, and so on is a sequence of n independent random variables that take values +1 and -1 with probabilities p and 1 minus p. Okay, and we can associate UI with meaning moving left or right at the ith step. We can take another random variable. We'll say that x takes values x1, x2, x3, and these are defined by xn is equal to summation I equals 1 to n ui. What would that be? If you think of UI as moving left or right by a unit distance,
Endpoint.
and you send from 1 to n, xn is the endpoint of a run, right? So the expectation of UI, well, it's 2p minus 1. Note that if p equals a half, then the expectation would be 0. The expectation of UI squared will be 1. And then the variance from the formula for variance would be 4p minus 4p squared. Okay. And then the probability mass function for these xi's is I choose I plus k over 2. So the probability that xi is equal to k is equal to I choose I plus k over 2. P to the I plus k over 2 times 1 minus p to I plus k over 2. Where k can go from minus I to positive I. Okay, the expectation of xi you should be able to work out is I times 2p minus 1. The variance is 4ip times 1 minus p. If it's symmetric like we were considering, where there's an equal possibility of moving either to the left or to the right, then p is equal to 1/2. And then the formulas simplify somewhat. The expectation becomes 0, the variance becomes n, and then the okay, so the variance becomes n. All right, so if we go back to our results. Yeah, so our estimation of the variance by doing this experiment was 1085. And the variance in terms of probability theory rather than statistics is 1000. So it's not bad. It's a reasonable prediction. Yes, there's a question.
Professor, I remember when we were discussing random walks with Professor Raz, he
Yeah.
mentioned that in such a model, the variance is unbounded, and so it's not very useful for us.
Yeah, if you're using it for, I mean, it depends upon the applications that you're using it for. Right. All right. Now let's consider a slightly more sophisticated model. We'll talk about random walks with boundaries. Right. So you could imagine that in some physics experiments, particles moving around in a box, and when it hits the wall, it gets absorbed and the random walk stops, right? So in this model, what we'll do is we'll say, I'm going to fix you're going to start at 0, and I'm going to fix an n. So you're going to keep doing this, this random step to the left or the right over and over again. And when you hit n, then the random walk terminates. Okay, so I know what the final state is. This final state is positive n or minus n, right? And what I'm interested now in is how long this takes, right? So you might be thinking of diffusion, random diffusion processes, for example. And I want to know how far it will take until the, I don't know, the oil spill reaches a certain extent, for example. That might be what you're trying to model. Okay, so again, let's do this multiple times and extract some statistics. I'm going to set the boundaries at n equals plus or minus 50. And so the experiment is going to be set the boundaries at n equals plus or minus 50, do 1000 random walks, and in each walk, when it hits either plus 50 or minus 50, then the walk stops, and we keep track of how many steps it took before you either hit plus 50 or minus 50. Okay, so get steps is as before, take steps is as before. We have a list, and we are going to we're going to perform each walk until we hit either plus 50 or minus 50. And we're going to have something called steps list, which says how many at every time we finish a walk, we've been keeping track of how long it's been taking. And so how many steps it took is put into my list that I'm calling steps list. Okay. And then we're going to extract the statistics from it. And it looks something like this. So if you're starting, say, from 0, and you're going to stop your walk when you reach either plus 50 or minus 50, then the minimum number of steps is going to be 50, right? Right? You can't reach n equals minus 50 in 25 steps, for example. All right. So anyways, there's a lot of walks that manage to take, I don't know, about 1,000 steps. And then there are very few walks that manage to take like 12,000 steps. Okay. And as I said, another thing that's of interest is the recurrence state. Do the same states happen over and over again? So one thing we might want to check is that if I start from 0, how many times does our random walker pass through the origin? Okay, so now we'll have another model. We'll start from 0, and then the walk ends when we hit 0 again. Okay, so and then we'll see what the results are for that. So basically, I've changed my boundary to 0 compared to the previous model. And if I do 1,000 random walks, and I start the walker going, and I kill the walk, I stop the walk when I'm back at 0, and I count the number of steps that it takes. So I did that with 1,000 random walks, and I found that on average it took like 4,800 steps. And you get this enormous variance in standard deviation. Okay, so there are walks which are taking a huge number of steps before you get back to the origin. Okay. All right. Now, if we use that probability that we discussed and a little bit of reasoning, what we would get is that the probability of getting a walk of length of getting back to 0 after 2n steps, that probability looks like KO. It's going as 1 over root n. Basically, that's the important thing. Okay. In 2 dimensions, it's going as 1 over n. And so here, the idea would be you have a grid, you have a square grid, and you can move by a unit distance left or right. And you also move by a unit distance up or down, right? For this walk. So you could imagine sort of 2 coupled random walks together, right? One is giving you the x coordinate and one is giving you the y coordinate. Okay. And then the probability of getting back to the origin after 2n steps is going as 1 over n. Okay, and in 3D, it's going as 1 over n to the 3 halves. Okay. So, there's a big difference in the behavior. This is an interesting thing in the physics. If we were thinking about pollen particles or some such thing. In 1 dimension and in 2 dimension, you should eventually get back to the origin. But in 3 dimensions, there's a possibility of never getting back to the origin. Okay. All right. So that was our very simple discussion about random walks and how you might implement them in Python. Are there any questions before we knock off for the semester?
No, Professor. Thank you.
Okay. Well, okay. In that case, what we will do is, okay, we'll get you some information about the take-home final in the next few days. Okay, so study hard and then have a nice summer break. Okay.
Thank you, Professor. You too.